It's my pleasure to introduce Nick Galatos from Denver University, who will speak on idempotent residuated chains.
Thank you, Jeff. So I'd like to thank the organizers for continuing the tradition of BLAST. This is joint work with my former student, Wesley Fostner. So let me start with the definition of residuo titularis, and then this slide will be devoted to mentioning where these come from and where they appear. So residuo titularis is just a lattice and a monoid on the same structure in a setting that allows us to solve inequalities of this form. So you can solve this inequality for the left factor, for the right factor b, by dividing away on the left by a, or you can keep the a and move away the b by dividing on the right by b, by means of these two operations that are called divisions or residuals. So let's see if you've seen these structures before or not. The name residuo titularis first appeared in the 1930s by Ward and Dilworth. They were trying to do point-free ring theory, namely just do as much ring theory as you can without looking at the elements, but looking at the ideals only. So the ideals of a ring do form a lattice. The join is just the sum of the two ideals. And we also have an extra product, the usual way you define it as finite sums of products of elements from the two ideals. And you also have the divisions. You can see them in usually books in ring theory. So this forms an example of residuo titularis. The ring itself is actually the multiplicative identity. And it actually is the top element of the lattice in that case, but that's no special thing. We assume the identity element could be anywhere in the lattice, and then we don't assume anything special about the lattice or about the monoid. Other non-commutative examples are also, we've seen lattice order groups in this conference, so all of those have this property, because division there is just multiplication by the inverse, as we all know in groups. But another example is relation algebras. In relation algebras, you have a lattice structure, Boolean algebra actually, and you also have another kind of extra operation, the multiplication. In this case, is just composition of relations. And it also comes in doubt if you think about it with two division operations that form a residuated pair or triple, as you can see here. So that's another example. Also, if you take the demand that the multiplication is actually the mid operation, if you reuse it, then you end up with a Browerian algebra. Browerian algebras with the bottom element are known as hiding algebras, and hiding algebras that have the double negation property are Boolean algebras. So you know residuo titularis because you know Boolean algebras. And in this case, actually in any case where the multiplication is commutative, for example here, the two divisions also coincide. And in that case, I will use this notation for the common value of the division of the quotient, which is just x r y implication as we use in logic. So the theme here is we try to unify, residuo titularis unify examples from both algebra and logic, and the divisions can be either multiplication by the inverse, division in groups, or just implication. Division and implication are the same thing for us. And it's good to use intuition from both perspectives. So they are general enough to form algebraic semantics for substructural logics. These are logics that come they are related to proof theory, and they, for example, relevance logic is motivated by philosophy, linear logic by computer science, many-valued logic maybe by engineering. They're also related to other parts of computer science and mathematical linguistics. So this is maybe where you have seen residuo titularis or where they appear. For this talk, I want to focus on the case of idempotent residuo titularises. So idempotent elements, we know whenever you have a multiplication like in semigroups or in rings, idempotent elements play an important role. And they also play an important role in residuo titularises. For example, the congruences of a finite residuo titularis correspond bijectively to idempotent elements that are also less than the multiplicative identity, and they also are in the center. They commute with everything. Also, in general, there are cases where residuo titularises have enough idempotent elements that somehow they form a skeleton from which you can think of the structure being built up with extra information. So it's worthy to study residuotitularis where every element is idempotent. So idempotency always refers to the multiplication, commutativity refers to the multiplication. So also, just for simplicity, I will start with the lattice structure being extremely simple, just being a totally ordered set chain. So we'll study idempotent linear residuotitularises and the variety they generate. So these are going to be subdirect products of the linear ones. So I will talk about the structure of all of the idempotent residue chains, trying to explain to you how they look like, how they're constructed. And then I'm going to have two applications. One is going to be the converse extension property, and then I'm going to talk about the amalgamation property about them. So that's the plan. Now, all of these results I will talk about today work in a slightly general, more general setting. In a chain, any two elements are comparable with each other if you only ask that the identity element is comparable with everything. So everything is either above or below the identity element. You have a conical shape, then I'm going to call this conic. So all of the things I'm going to talk about work about the conic ones and the variety they generate. But for simplicity, I'm going to just restrict the totally ordered case here. So some examples. What are examples of idempotent residuity chains? Start with any chain. Take, for example, the integers here, and name the elements b sub the integers, and order it the usual way. Take another copy of the same chain, but upside down now. Now, use A for above, and B I'm using for below the identity element. And I'm ordering now the A's, the above elements, downwards. So the indices grow as you go down. So that's the lattice structure. What is the multiplication? If you have any two elements and you want to multiply them, you pick one of the two, the one that's furthest away from the center, from the identity. So you have a notion of distance. I'm assuming everybody knows how far something is from the identity. If you have elements, take the furthest away. If there's a tie now, for example, A0 times B0, then break the tie by picking the smallest of the two, pick the element that's below the identity. So this gives you an example for residuotitularis. It's known as an odd Sugihara monoid, an odd Sugihara chain. And you'll see these start elements here that I have here. These are the result of applying to the B's, the star, or to the A's, and they take it downstairs. The term x star is just xr1. So this is just the inverse. It's the inverse of an element. And as I think we saw, Sarah defined the absolute value in the null group. We define it also here. It's just x joins x inverse, and this is always a positive element, and it measures distance. So you can define distance if you just have the order and the star. Therefore, you can determine the multiplication just by this inverse operation and the order, and also actually the divisions, or the arrow in this case, because it's commutative, is also determined. So that's the only thing you need to know is these two things. And you can abstractly characterize the variety, axiomatize the variety as the ones where the double star gives you what you had. It's generated by chains, and it's idempotent and completely. And these were studied by James Raftery because they're models of relevance logic, or at least one type of relevance logic. I want to give another example that's going to be non-commutative. So considered those back in 2004 because I was trying to give uncountably many atoms in the subvariety lattice of residuotitularises. So these generate, enough of them generate uncountably many. So now do the same thing, take any chain, but now please take the chain to be discrete, namely either the integers or the naturals or the duals of the naturals or a finite set. And do the same thing, flip it upside down up there and define exactly the same thing, the product to be the furthest away from the identity, but break the ties in a different way. We have to be given an index set, subset of the index set, that's going to tell us how to break the tie at every single point, and it may be different for different points. You just look at the place where you have the tie, and then you break it if the element, let's say, is in the given subset. You break it by picking the left factor consistently, or if it's not, you pick the right factor. You can't do what you did before. You can't pick the smallest element for both products. The results of the two products have to be different. So it's not commutative at every single one of those cases. We have two now inverses because it's not commutative. So we have the left inverse and the right inverse, if you want, the L and the R. And you can see how these behave, but one of the things that we lose, for example, is local finiteness. In the previous example, if you have an element and you want to generate the subalgebra, you only generate the element, the star, and the identity, and these three elements give you the subalgebra generated by this. So it's very locally finite, but here, by any non-identity element, you can generate the whole thing just by applying these L's and R's. They take you everywhere. So it's quite a different example. But you also lose the involutivity, the fact that if you combine one inverse with the other, it gets you back. You don't have that anymore. And the divisions are not expressed in the previous way, but they are definable, first order definable still. So I'm going to get back to this example in the end of the talk. One of the things you could do with either the commutative or the non-commutative is to shove one inside the other. So think of the black one sitting outside, and you have the identity, remove the identity of the black one and put in its place the blue one. And I call this the nested sum construction, and it always produces an idempotent residuated chain here. And if you do that with the three elements Sugihara monoid of the commutative case, repeatedly you can get all of the commutative Sugihara monoids this way, because just get this arbitrary chain in the bottom that you want. I'm going to skip the formal definition. Another thing you can do is, in the commutative case only, safely, is the following. You can start with the Sugihara, odd Sugihara chain, and you can hang from any element between those two adjacent elements. Below this one, you can take any chain, A sub AI, and put it there. Any chain of elements, just put it there in any place you want, or as many places as you want, as big chains or as small chains as you want, and this also gives you another one of those. So it's the ordinal sum of all of those chains, and the original algebra S, the Sugihara monoids, forms its skeleton. Now, it was shown by James Rafter and also by Peter, Jose, and George that this is all there is. This way, you can get all of the commutative ones. Start with an odd Sugihara chain and hang those pieces, and then you have the result. And how do you do that? You do that the way it's explained is by a closure operator. The star forms a Galois connection with itself. So apply twice, and what you end up doing is you take an element of this chain, and by double negation, you end up sending it to the top of the chain, of the local chain. So that's a closure operator. It's more than that, it's submultiplicative. That's called the nucleus. But the image is the skeleton. So this gives you as an image of the skeleton, and as pre-image of every point, you take a fixed element of the image, and you look at all of the elements that double star to that point. That gives you exactly the local chain, and you get the decomposition. And that's the end of the story. That's all there is. So I would like to do the same thing for the non-commutative case. So again, this is the formal definition of a nucleus. It's just a closure operator that is submultiplicative. And these gadgets are useful in residuated lattices. Always the image forms a new residuated lattice, adjusted a little bit. You have to close up a few of the operations to get you back to the center. So let's do the same thing. Now we have two inverses. They form a Galois connection with each other. So we actually get two closure operators. You can apply the LR or RL. They both give you a closure operator, none of which, unfortunately, is a nucleus. So there's no guarantee that the image is now going to be a residuated lattice. And I think that's maybe the reason why there was a little bit of trouble getting a full description of these since these examples at least were done. So there's a lot of literature in between, and very useful ideas and so on. But I think a full transparent description was still lacking. So let me just explain to you how to deal with this problematic situation here. The idea is So to really think of these inverses, because this works, it adapt mainly more a semi-group theoretic or monotheoretic approach, but I want to bring back the inverses into the study. So, and also, I'm going to use some notation further in the paper. By asterisk, I will denote the bigger of they're comparable, so I will denote the bigger of the two inverses, and by star, I will denote the smaller of the two. But this is coming up later. So I want to take the set of all inverses, left inverses and right inverses together. This is a set of all inverses. And the map that has this inverse is actually the meet of the two closure operators. That's the guy we should be taking. And that one is a nucleus. The meet of the two, both of them fail, but the meet does work. And the image is precisely the set of inverse elements, left and right. And the pre-images give you exactly the chains. So that's the whole decomposition. This result to prove actually that the nucleus, especially in the conic case, it takes quite a bit of work, but the answer is very pleasing. And then the skeletal ones, they are the ones that have a nucleus that fixes them. So you get this identity for those elements that we call quasi-involutive, because you don't have that RL gives you the identity or that this, but the meet of the two gives you that. So that's quasi-involutivity. The skeletal objects in the non-commutative case are the quasi-involutive ones. So yeah, that's the decomposition. So this is enough for my first application here to talk about the congress extension property. The congress extension property says that if you have an algebra and you have a congress in a sub-algebra, you can extend the congress to a congress of the whole algebra, so that if you intersect, you restrict exactly to the congress that you have. You don't pick up new elements this way. So congress is now in residue Laplaces. We heard that in groups, we were reminded that in groups, congresses correspond to normal subgroups. We know that in Boolean algebras, congresses correspond to filters. This is somewhere in between groups and Boolean algebras, so it's not a surprise that you can also get rid of congresses, just focus on the specific subsets. What are these subsets? They're filters, like in Boolean algebras, but you have to be also a submonoid, closed under multiplication, continuity, identity. And like in groups, you have to be normal. You have to be closed under conjugation. We don't have an inverse, but we can still have division, and they do the same job. So these are the congruence filters, and then you can move back and forth between the congruence. You can take the congruence class of the identity, look up, you get one of those. If you have one of these, you can say that two elements are related. How do we do it in groups? If X inverse Y is in the normal subgroup, in that case, also Y inverse X is in the subgroup. Or if you want, as we do it in Boolean algebras, two elements are identified if X ROY and Y ROX are true statements. So logic or algebra give you the same thing. So the result here is that, the problem with the congress extension properties is this parameter A, because the parameters may come from the bigger algebra instead of the sub-algebra, and they may give you more elements that you have to worry about. And you don't need this parameter. This normality condition is automatically satisfied in the commutative case. But in the non-commutative case, like in groups, you need these conjugates. So even though we have non-commutativity here, we can still control the conjugates. You can't get away with removing them, but you can control any conjugate of the element Y by any conjugating element X simply by versions of Y. So from below, and that's all we care about, by Y, it's double inverse L and it's double inverse R. If you meet these three elements, you'll get know enough to control all of the conjugates of the element Y. So we can control the behavior of the conjugation this way without parameters, and therefore easily we can prove the congress extension property. For the corresponding substructural logic, this gives you what is called a local deduction theorem. So you get the corresponding logical application from this. Okay, so let's go to the second application of amalgamation. Now we have to work harder. We have to understand the structure of chains much more deeply, because we have to understand sub-algebra generation in the non-commutative case. And because everything is generated by these L's and R's, the only thing I have to show you is how do these two unary operations move you around the algebra. So there are only three cases. Either the element you have is central, it commutes with everything, or it forms a left zero semigroup. That's the motivating example from 2004 paper shows that we pick left in this case, or you pick right with one more element and you commute with everything else. So the non-commutativity happens locally only with one element at most. And in that case, the element you're from a left zero semigroup is always the asterisk. It's always the bigger of the two inverses. So it's either the L, if that's the bigger, or the R. Two cases, the blue and the red. And in that case, we can know exactly the whole flow. So here I'm using dotted lines for the L unary operator and solid lines for the R. So for example, here you can move with L here, and then you can move with L here, or from this element, the element B below, negative, you can move with R and then R here. And the thing to observe here is that what I mean by this solid line, this solid line now is a covering pair in the ordering. So from flow information of the unary operations, I can link it to order information about the algebra. These two elements, the L and the R, always form a covering pair. So what I've done here is you can see here the negative elements ordered, essentially. And what I've done here is I've broken the positive elements and I moved them closer so that I have this nice link between those two elements because they match up. And this is the reverse order on the positive element. This ties very well with the monoidal preorder that was considered by Peter, Jose, and George, that defines x to be preorderly smaller than y if x times y is x. And this is the drawing of the preordered set corresponding to this algebra. This is the monoidal preorder. And as you can see, what it does is you look at the algebra from above. This is the center, and then these are concentrically moving out as you go down. So you look at the algebra from the center, and you take the identity and you pull it up, and then the other fall down next to it. And this is a preorder, so how do you draw preordered Hasse diagrams? I put horizontal lines, which is a no-no for my students. But it's a preorder, not an order, so I can have the line or not, if they're incomparable. Now, this information along the monoidal preorder considered in their paper is not enough to distinguish between these two algebras. For example, it doesn't know if the element C3 is positive or negative, just by knowing how far away it is from the identity. So we enhance this. We throw this extra information of telling every element if it's positive or negative by using another dimension, the horizontal dimension, and lining up the positives on one side and the negatives on one side. So we get these pictures of enhanced monoidal preorders now, where all of the negative elements appear on the right and all of the positive on the left. And you have these rhombus-like figures that are tilted a little bit to the left. And that's important because it tells you a lot about the subalgebras. Now, I can see one of these things, and immediately, just go here, I can superimpose, and I can see the flow diagrams appearing inside just by superimposing those two pictures. So these pictures here give me all of the information I want because they tell me how the L and the R work, so they tell me how subalgebras are working. Not any one of those pictures will give an algebra, and that's something we had to work out. The condition is that for every element B, let's say here, and it automatically holds in the finite case, but not in the infinite, there has to be a smallest A, in this case, the one corresponding to B3 is going to be A5, a smallest A that's going to be strictly greater than B in this monoidal preorder. And conversely, for every A, there has to be a biggest B corresponding to A5 will be B4 now. That's going to be the biggest negative element below it in the monoidal preorder. So this gives rise to this description here. These are the two conditions I just mentioned of when such a thing will correspond to such an algebra. So that was the missing piece, and also a formal definition of what it means to be layered. So we have these enhanced monoidal preorders, but we can draw them. We know exactly which ones correspond to actual algebras and we can work with them. So for example, let me just say here that if I have two of these algebras and I want to know when the corresponding preorders when one is a subalgebra of the other, I just look at the corresponding P sub A, and P sub A has to be closed under same level elements, under the star, and it has to contain 1. Star is this operation that I mentioned, that it picks up the smallest element above or biggest element below, and it matches with the definition of being always in the lattice order, the smaller of the two inverses. So I have a clear description now when I have subalgebras, and I can do amalgamation. So I'm going to skip the definition of amalgamation. I'm just going to say that there's bad news, amalgamation fails. For chains, if you have two idempotent chains, you may not be able to amalgamate. Why is that? Here I have a B and a C in a common subalgebra A, it's the one element one. And the problem is B3. B3, the star of B3 jumps to 1, by L actually in this case, and B3 prime also jumps to 1, but somehow from the rest, they don't behave the same, and then you can discover it. And it would be a clash if you could amalgamate the two. So that's a problem, and okay, amalgamation fails. How can we remedy the situation? Well, first of all, there's even worse news. Amalgamation fails even if you try to amalgamate in the variety. You have two chains, and you don't necessarily want to amalgamate them with a chain, but with any algebra in the variety. That takes more work to show that. But the problem is, because the X star, it happens every time. You jump into a blue subalgebra by something that's outside of it, by doing star, without being able to escape from there back. And here, of course, this is the one element, it's the identity. If you start with, you're stuck there. So you have to be able to go back. Every time there is a feature where you have a subalgebra and some element stars inside it without being able to escape back to that element eventually, you have a failure. I can produce a failure of the amalgamation. So the natural class to consider is the case where this doesn't happen. And we can prove that if you eventually go back out from the subalgebra, you actually also will be able to go back immediately. So the condition to consider is the double star. The double star of every element has to give you back the element. You have to be involutive with respect to this star. Again, the star is the smallest of the L and the R. And that's the condition that we impose. We just need this for the skeletal elements. So we just say that every right inverse is double star fixed and every left inverse is double star fixed. This gives rise to a condition that we just call rigidity. So idempotent rigidity chains that are rigid, namely their skeletons are star involutive, are the ones that amalgamate well, or are expected, have a chance of amalgamating. And what are those? These are exactly the ones from the 2004 paper. These are the two cases, the Z, the N dual, and the finite set. So this is how they look like. These are all of the star involutive ones that are generated by a single element. All of the others are nested sums of them. So we are fully able to understand the subalgebras of this. Actually, this is generated by every one of its elements. So amalgamation now is completely transparent, and we can prove that you can actually have the strong amalgamation property for the skeletal ones. And then you can amalgamate every time you have two idempotent chains. You can pluck out the skeletons, amalgamate those, and then locally amalgamate all of the chains. So therefore, we have the strong amalgamation property for all idempotent rigidity chains that have this rigidity condition. And then using existing work in the literature, we can extend it, and also the converse extension property that I mentioned before. We can actually extend this to the strong amalgamation property for the whole variety that's generated by these idempotent rigidity chains that are rigid. And then this has consequences. The strong amalgamation property is the combination of the amalgamation property plus the epimorphism subjectivity property. The amalgamation property for the algebras gives you the bed-definability property, gives you the interpolation property for the corresponding logic, and the epimorphism subjectivity for the variety gives you the bed-definability property for the corresponding substructural logic. So that's how we get the corresponding results for the logical systems. Thank you.
Do you have any questions?
So, just to check, I mean, in the commutative case, this is rigidity is the same as involutive, or
Yes.
okay. Interesting.
Well, so it's not the same. No, it's yes, it is. It is exactly. So these results specialize also to the commutative case, and they give you exactly specialized to give you exactly the skeleton is a Sukihara monoid in this case.
Did you say something about the conical ones? I mean, the last part was only about linearly ordered, right?
Yeah. So exactly the same results works for the conical. Because for the conical, we have the same nucleus, the double, well, it's the LR meet LR, and then it takes much more work to show that it's a nucleus, but once you do that, then you have the decomposition for the conical. So we pluck out the skeletons from the two conical, we amalgamate those, and then we have to worry about the we have to study the structure of the conical ones, and they end up being bubbly, like bubbles, not just at one. And then you have to understand what the bubbles are, and the bubbles are on the negative part, they are hiding algebras. On the positive part, the bubbles are lattices where you may have been missing the bottom element. But both of these classes have the strong amalgamation property. So you can strongly amalgamate each one of the bubbles separately and then put the whole thing together.
Yeah, one more.
So I guess from my perspective, the obvious question here is, since you have amalgamation, there's a universal object there, like a Fresnel limit. Is there like any description of that? Or yeah.
So what do you need? You need amalgamation plus what else do you need?
Joint embedding property. So whenever you have
joint embedding properties, which is a consequence of this.
Amalgamation if the empty
well, we have one element algebras here, so we're okay. We have the joint embedding property. Yes, so we have Fresnel limit. Yeah. So no, I don't know what it is, but
because the amalgamation is strong, this means that it will have a very rich group of symmetries.
Yes. Yes.
And in this period, also you mentioned a non-amalgamation result.
Yes.
But there is a property called weak amalgamation, actually, which perhaps, I mean, one has to check if, because it's possible that if it satisfies weak amalgamation, still you can build something like a generic.
There's still some model theory you can do even with weak
sort of weak Fresnel limit. So the question of if the previous class, before you put the star, before you put the side test for the star, maybe still it satisfies the weak amalgamation.
The weak amalgamation, yes. Thank you. Yeah.
Let's thank the speaker and go get some coffee.